Hello and welcome to day 17. So today we have a shortest path problem. So we want to find the shortest path between the top left node and the bottom right node. So normally we use Dijkstra's algorithm for this. So basically that is you start your start and then you add your total path on to a priority queue or some other sort of queue. So we would add all the adjacent spots. So we add 4 as our total length is 4 and we add 3 because our total length is 3. And then the next node we visit is this 3 because that has the lowest total path so far. And so we add all of its adjacent nodes. So we add this 2 because, which is actually going to be a 5 total path. And we add this 3, which would be a 6 total path. And then the next one we have to do is we have a 4, we have a 5, and we have a 6. So we would do the 4 next. When we come back and do this 5, we see that the 4 is adjacent, but there's a shorter path that we already know about, so we're going to skip it. Basically, by doing it this way, when we're done, we'll have a shortest path to every potential place on the grid, and then we just have to look up which one we care about. Now, there's a couple caveats with this. It's kind of Dijkstra's algorithm with extra steps, because we aren't allowed to go in the same direction more than 3 times. And we can't backtrack. So like if we ended on this one, or if we ended on this one, we can't go back to this one just to go forward 3 steps again. So we would have to, take a turn and like kind of U around or something like that. Those kind of make it a bit more difficult. So for part 1, the first time, so we kind of have to keep track of our state in addition to our total length, because if you have a node here and you come to it from the left or you come to it from like below, that could give you different answers. So even if the below might have, say, a higher total score, it may be better because I can go left 3 times, as opposed to if I came in from the left, I might be only able to go once or twice. So we have to keep track of how many steps we've taken, and we have to keep track of the direction that we're already heading. So I added a node class, and then I made a list of nodes, and then just basically added all of them in there, and started at the start. And then for everything our queue is basically just going to be the lowest, and I'll just take that every time. And then for each item, we'll go through there and find its neighbors and update. This is slow. I mean, it was fast enough to get to the first part, but slow enough that it was obviously not going to work for the second part, and not something that's going to really be kind of good code, I guess. So what I did instead is first I pulled out the get candidates into a separate function, and then the way I'm going to do this is every time we land somewhere, we assume we have to turn. So if you're going forward, then you can't go backwards because you can't reverse, and you can't go forwards because I'm assuming you have to turn. So you either have to go left or you have to go right. And then as far as our steps, I'm going to take 1, 2, and 3 steps. So I'm going to go, if I have to take a left or whatever, then I would take a left 1 step, 2 step, and 3 step, and I'd add all 3 of those to our queue. And each of those, like if you only take them 1 step, we're assuming you have to turn because the other 2, forward moments at that point are already accounted for. This reduces the search space quite a bit. So basically this function, we'll just go through there, and if you're not going back and you're not going up, then we'll add in up, and the same with down and left and right. This can be a little bit shorter, but it's fine. And then at the end of this, I'm just going to remove all of them that fall off the grid. So easy enough. And then for our update here, a couple of things changed. So instead of using a list and finding the minimum, because this list was getting hundreds of thousands of items long, and it takes a while to sort that. I mean, doing it once is not that big of a deal. Doing it, millions of times starts to really slow down. So instead, I'm just going to use a straight priority queue of only nodes that we have marked but not yet visited. While the priority queue is not empty, we're going to take our first one out of it. If it's the last item in the thing, we're just going to break. We don't need to continue to find anything additional. And then we're going to grab our candidates from that function I just showed you. And then for each candidate, if the candidate already exists, like if we've already seen this node, and we're not the shortest, we're going to skip it. If we haven't seen it, or if these are all going to start at the max values, so always have just basically infinite for shortest if they're not. But if we haven't always seen it, or our new path is shorter, then we're going to update it and add it to the priority queue. And then at the end of that, we just need to find our lowest for the last entry. Now, one other thing I did to make this a lot faster is instead of using a mutable list, I am using a three-dimensional array. So it's an array of 4, which basically each direction is an array. So you can think of it like an X by Y grid. And I just have 4 of them stacked on top of each other. So if we're going to use the up value, then I'm just going to take like the up grid, the first one, and I'm going to look at just that grid. If I'm taking the left value, I'm just going to take that third grid or whatever and pull that one out. And so that's why I have this part here where we need to take the min of those 4 grids. But that way we still keep track of our direction, and we also keep track of all of our shortest ways to get there based off of which direction we come in. So that was quite a bit faster. Like from like 20 minutes down to under a second faster. So for part 2, the difference is that now we need to go a minimum of 4 blocks in each direction and up to 10 blocks. So every move has to go 4, 5, 6, 7, 8, 9, 10 blocks. You can't go one in turn. And then one tricky part here is if you read quickly, you have to end on a 4, 5, or 6 block or something like that as well. So on that one, since this part has already been kind of fixed up here, the only parts I did differently are the candidates functions now, where if it's for 1 to 3, I just add them up because I need to know how much distance we go through. And then I add candidates for 4 through 10. This is a lot more candidates, obviously, and if you have kind of a bad algorithm, this is not going to finish today. So that's pretty much the main difference. I think everything else is basically the same. I don't think there's anything else that changed. But after making those changes, it runs much, much quicker. We'll see here after it compiles. Yeah, so you know, in the 100 millisecond range. Anyway, hope that helps. If you've got any questions, of course, hit me up in the comments. I have the newest code on the GitHub as always. And other than that, I will see you tomorrow.